Now let's talk about gas refrigeration. So when they talk about gas refrigeration, this is ideal gas. And it's really the Brayton cycle run backwards. So you're going to have a compressor in the Brayton cycle run backwards. And you're going to come out of the compressor. This time we're going to show it going in this direction into a heat exchanger. After the heat exchanger, we'll run it through a turbine and then into another heat exchanger. Weren't those the 4 components of the Brayton? But this bottom heat exchanger will be one in which you are absorbing heat. Heat will be added. Okay, so this is maybe Q or Q dot coming into the system, and this is where it's going out, Q dot out. Now, if this would have been a vapor compression refrigeration system, we would call this heat exchanger either the condenser or the evaporator. The evaporator, right. And this one on the top, we would typically call the condenser. But the ideal gas is not condensing. The ideal gas is not evaporating. Okay? But we do have a heat transfer. Let's go ahead and number 1, number 2, number 3, number 4. So those are our states. Tell me a little bit about the pressure. If I look at this side, is the pressure at 2 equal to the pressure at 3? That's our standard assumption, sure. Compared to the pressure at 1 equal to the pressure at 4, which one's high? Is this the high pressure? Yeah, so we only have 2 pressures, high and low. All right. Now think about our temperatures. Compare temperature 1 with temperature 4. This is a clicker question. Is the temperature 1 greater than, answer A, equal to, answer B, or less than, answer C, than temperature 4? Just compare temperature 1 and temperature 4. Is the temperature 1 greater? Select A. Is it equal to? Select B. Or is it less? Select C. Everybody in? All right, let's take a look. All right, so temperature 1 is higher than temperature 4 because you're adding heat. If you're adding heat into an ideal gas, is the temperature of the ideal gas going to change if you add heat to it? In the ideal gas, it's not changing pressure, just adding heat? Yeah, it's going to go up. It's going to go up. So A is correct. All right, let's ask a similar question. I would like to compare the temperature at 2 versus the temperature at 3. Is the temperature at 2 greater than, answer A, equal to, answer B, or less than, answer C? How does T2 compare with T3? All right, we're down to the wire. Okay. Well, what's happening here? Heat transfer out. So let's see how well we did. So T2 is greater. It's being cooled, is it not? T3 is less. All right. I'm not trying to be tricky here. All right. Now let's do this one. T1 versus T2. What's happening as I flow from 1 to 2? What's it going through? The compressor. All right. Is T1 greater than, answer A, equal to, answer B, or less than, answer C? Compare those two temperatures, T1 and T2. Which one's higher? Which one's lower? So let's take a look. So what happens to the temperature? T1 is low. You're putting a lot of work into the compressor. It boosts the temperature because it's putting work in to boost the pressure. So, why do I not get closer to 100% correctness? I don't know. All right. Well, let's do this. let's say that I'd like to sketch now a property diagram. Once we have the components and the states identified, some sense of what the pressures and temperatures are, and the property diagram would be a temperature entropy diagram. What would be a line of constant pressure for an ideal gas? It's ideal gas. Don't worry about the dome. Tuck the dome way down here. Get it out of the way. You know, it's ideal gas behavior. What does a line of constant pressure look like? Put two of them on. There's one. Well, let me make it a little steeper. 1 and 2. Which one would be the high pressure? The one on top? Yeah, from our experience. So this would be the high pressure. This would be the low pressure. Now we can think about, where's going to be our states? Where's state 1 and where's state 2? It takes a little bit, but state 1 is going to be here. It's relatively warm at the low pressure compared to state 4, is it? And then when we put it through the compressor, it's constant S, unless I have some efficiency, then it would kick it over. True. But if it's 4, let's say it's isentropic efficiency, the compressor is 100%. So I know that I could have a little kick over. And then, I'm sorry, that's 2. Thank you very much. And then we come down and we stop cooling at 3 because it's going to be reversible expansion through the turbine. Now, what happens, where would be state 4 if it was the compressor, the turbine had something less than 100%? How would it change the diagram? It would kick it over like that, wouldn't it? Right, but we're going to have a isentropic efficiency of both the turbine and the compressor be 100%. There's our standard Brayton cycle. When it's run this way, where do we have our heat addition? From 4 to 1. That's where the heat is coming into the fluid. Where do we have heat rejection? 2 down to 3. So you have to kind of have it dumping to the temperature of the high sink needs to be lower than T3. Otherwise, you're going to have some problems, true? And then you have to have also the temperature low where you're picking up the heat needs to be higher than T1. Otherwise, it's not going to get it all the way to T1. Right? Okay, so that's good. So this was our illustration. Yes, you don't have to supply all of the power to the cycle because that turbine will produce some which will help drive that compressor, but there will be some net power to make the refrigeration cycle work. There will be some net power. All right, now what I want to do is not solve that problem. Somebody says, we were introduced to the Carnot and it had a turbine. And then we said, this turbine's not going to work so well. We'll still leave the compressor in our vapor compression refrigeration. But what we're going to do now is we're going to just substitute an expansion valve in there. The basic question, if I replace the turbine for a gas refrigeration cycle with the expansion valve, will this work? Will it work? So this is a clicker question. A for yes it will, or B for no, it will not work. 30 seconds. And I think you see the clicker timer, right? Oh. So we're done with that, huh? So good? Everybody's in? Well, let's do this to explore that. Let's do this to explore that because let me show you the results. And that's not too surprising for me. But I'm going to not grade that right now. I'm going to come back and grade that. And what I want to do is I want to talk about the relationship between the properties at 3 and the properties at state 4. And I encourage you when you're new and you're learning thermodynamics to say, just list all the properties that I know. Okay, well I know about temperature. And I can think about the temperature at state 3 and the temperature at state 4. And you know what? We just explored that relationship, didn't we? Was temperature at state 3 equal to, greater than? But now we switched it to an expansion valve. We have to re-explore the relationship between T3 and T4. But let's make our list. Pressure at 3, the pressure at 4. You could put the specific volume at 3 and the specific volume at 4, but you know what? That's going to be needed if I need to size my tubes or whatever's handling the flow so it doesn't go too fast, trying to push a high mass flow rate through a small tube or a low mass flow rate through a large tube. And I'm going to say that we just don't need that right now. Likewise, U3 and U4, because it's an open system analysis around that, I really don't need to emphasize U3 and U4, but everybody knows about H3 and H4. And then the last is S3 and S4. So I just want to compare these. Let's do this. If I look at let me do this one. Do it just like this. H3 compared to H4. Is it greater? Answer A. Equal? Answer B. Less? Answer C. 30 seconds. The enthalpy at 3 compared to the enthalpy at 4. Well, this proves that the class as a whole has learned a lot, either in Thermo 1 or Thermo 2, somewhere along the line, because a lot of people would get this wrong. But it's isenthalpic. Oh, there's some steps in reaching that conclusion, but you've done it enough times. Where's the starting point? Control volume, conservation of energy, negligible change in kinetic potential, no heat transfer in, no work transfer. There you go. But a lot of people will argue with me on that ad nauseum. I'm just tired of arguing. Okay, stick with whatever analysis you want to process in your brain. But H3 is equal to H4. Let's do this one. How about S3 compared to S4? You know, which one is it? The entropy, S, at state 3 compared to S4. All right, so let me ask this. Sigma dot, what does the symbol sigma dot represent in this textbook, in this class? Entropy generation. Is sigma dot equal to 0 in the expansion valve? No, it's not. Meaning flow through the expansion valve is irreversible. Irreversible, there's entropy production. So after I do a second law analysis, same control volume, can I show that S4 is equal to the incoming S3 plus sigma dot divided by m dot? Have you done that enough? Does that equation make, music to your ears? True? Why is that not more than 72% correct? All right? Okay, let's press forward. Okay, so S4 is greater than S3. True? All right, what about the pressure? Let's, should I give you 30 seconds on that or not? We already did it, right? Which is the high pressure? Is this correct? Yeah, now the temperature. Tell me about the temperature. That's the critical one. Give me your answer for the temperature. All right, let's review a little bit because let's do this. Okay. If it's an ideal gas, there's 3 things that should pop into your mind. Say, oh, this substance is an ideal gas. You should say right away 3 things. One of them is P, V equal RT. That's an equation. It always applies for an ideal gas. All right. One other thing. Do you remember it? Do you remember it? Do you remember it? Front row doesn't remember it. What other thing do you remember? I tried to emphasize this again and again. 3 things to remember. R is constant. No. Something about U and something about H. What about U? What about H? U is only a function of temperature. Enthalpy is only a function of temperature. All right, I'm going to re-ask the same question. Compare T3 and T4 now that you've been reminded of these simple facts about an ideal gas. All right, Because it's isenthalpic, and H for an ideal gas is only a function of temperature, what do I know about the relationship between T3 and T4? B. They are the same. Now, that's the second answer to the group, but this was the first response to that question. One person, this is humiliating for me. This is humiliating for me. It's like, did I not emphasize U is a function of T only, H is a function of T only? All right, so let's do this. We've graded both of those. Will this work? I didn't go back and grade the will it work, did I? But you put it on a property diagram. This is a high pressure to low pressure. State 1 to 2, it's going to be a perfect compressor. Let's not change that. Let's cool it off down to state 3. And now if it would have been a perfect turbine, that's where 4 would have been. But where now is state 4? Is it going to be somewhere in here, somewhere in here, somewhere in here, or somewhere in here? Answer A, B, C, or D? On a TS diagram. Yes, this is a T temperature entropy diagram. Where is the new state 4 when I put an expansion valve in? Everybody in? Sorry I can't give you more time, but let's see. Constant enthalpy, significant increase in entropy. Temperature's got to be the same as T3. Horizontal line over. There is state 4. It's closer to section D. Is this refrigeration cycle going to work? It's hot going into something that's supposed to absorb the heat. So we go back to our original question. And we say, will this system work? Yes or no? The guessers had it. The bees had it. Thank you for your attention. We're all done. I'm out of time. Thank you.